Today we are going to speak about a concept that brings together, in a sense, set theory and category theory. So we mentioned from the beginning that the point of category theory is to try to do mathematics without knowledge of elements of structures, just knowing what the structure preserving maps are and the structure of their composition, but not necessarily knowing what the elements of the structures are. But it turns out that with this step of abstraction, we're actually, this step of abstraction can actually be presented also as something that still confines us within a set theoretic realm where we do know what the elements are, except that now elements behave slightly differently. So I would like to, there are many ways to begin this topic, and I would like to begin in a certain way. It might not be the best way. And some of you might have already seen this idea before, the idea of a variable set. So basically a variable set is a set that changes its constituent. And this change is parameterized by morphisms of a certain category. Now, instead of beginning with an abstract notion of a variable set, I want to begin with a very specific notion of a variable set, which is based off on a given category. So let C be a category. And let us consider an object X in C. And I want to claim now that we can regard an object X in C as a variable set. So in an abstract category, we can't speak of elements, but what we can do is to consider another object C, and then consider morphisms from C to X. There is a traditional notation for this construct. Hom Cx represents the collection of morphisms from C to X, but assuming that our category is such that for every two objects, morphisms from that object to the other one forms a set, so it's not too large, then we can speak about the set of morphisms from C to X. And this is inside a given category C. And sometimes one appends this subscript to hom to indicate in which category we are working in. But since we are going to be working mostly in one category, I'm not going to do that. I'm going to drop that subscript. Now, this set of morphisms, I want to think of it as the set of elements of X. So X is fixed here. So we started off with a fixed object in the category. And I want to think of elements of X to be morphisms from C to X. In fact, there is even an official term for this. It's called a generalized element. An element of hom Cx is also referred to as a generalized element of X. But of course, this set, hom Cx, is not fixed, even though X is fixed, because C could change. So for every different C, we will have a different representation of X as a set. And this is where the idea of a variable set comes in. There is, however, a way to link different Hom sets for a fixed X as we vary the C. For example, if I consider now another object C prime, there could be a way of comparing Hom Cx with Hom C prime X. We would have such a comparison every time we have a morphism from C prime to C. So let this morphism be F. And then if I take a generalized element of X, let's call it small x, what I can do, of course, is to compose F and X. And this gives a mapping from Hom Cx to Hom C prime X. This mapping also has a name. We can call it Hom Fx. So what does it do? It maps a generalized element X to the generalized element XF. Okay. So if now I want to formalize this idea, so what kind of mathematical structure do we get out of this? The answer to that question is that we actually get a functor. Because you see, we've described what to do with every object C. We say that we take a set and associate it to every object C. And we've also described what to do with every morphism F. We have a certain function associated to it. So we get a functor into the category of sets. But what is the domain of that functor? You see the direction of arrows has been reversed. F was a morphism from C prime to C, but now the function that we produce out of F goes from the value of the functor at X back to, at C back to the value at C prime. But a functor cannot reverse direction of arrows, right? A functor must preserve direction of arrows. But there is a way to remedy this by considering the dual category. So what I get here is a functor from C op to the category of sets. Let's get convinced of this. So in general, what should a functor from C op to set do? For every object in C op, it must produce a set. In our case, this is the set Hom Cx. Remember, X is fixed. Then also what a functor should do is that for every morphism in the category, so if I have a morphism in the category C op, going from C to C prime, so this is happening inside the category C op. We're not thinking in terms of the C category yet. We're thinking in terms of the category C op. So in C op, let's say we've got a morphism from C to C prime. Then a functor must map a morphism to a morphism in the other category. So of course, in the category of sets, morphisms are functions. So it must map the morphism F to a function from Hom Cx to Hom C prime X. So that's what f of f should do. However, a morphism f from C to C prime in C op is the same as a morphism f from C prime to C in the category C, right? So this is happening in C op, but a morphism in C op is the same as a morphism in the opposite direction in C. And hence, indeed, we do have a value of the functor at such a morphism. It is our Hom fx. Once again, what does it do? It maps x to the composite xf. Okay, so that's what a functor should do structurally. It must map objects to objects and morphisms to morphism, but also it should preserve certain things. Namely, it should preserve composition and identity morphisms. So let's check that it does. If I compose two things on this side, let's say f and g, and then map by the functor, I must get the composite of whatever functor maps these two things to. And of course, reminding ourselves that a G would be another arrow going backwards in the category C. F of G will be again Hom Gx. And now we're going to draw what is F of the composite of G and F. So the composite GF will be mapped to a function here. Well, the composite of G and F in the category C op is the same as the composite of F and G in the category C, right? But everything now going the opposite way. So F of this composite of GF will be Hom FG X. Okay, so now we are ready to check that F is a functor, at least that it preserves composition. Preservation of composition should now be that if I take an element X in here, maybe I'll use a different color for that. So if I take X in here, I map it down along the composite of these two functions. That should be the same result as mapping it along that bended arrow we've got here. So what happens if I map X down by F of F? Well, we know what happens there, and X gets mapped to XF, right? And then when we map this further along Hom GX, so the pattern here is that the arrow gets attached to the right side of the element, right? So the G will be attached to the right side of XF. So it will be XFG. On the other hand, with the other mapping, X will map to, trying to find space in which I can draw this. With the other mapping, X will map to X with FG attached to it, right? Are these two things equal to each other? Well, it's exactly associativity of composition of of morphisms in a category. In a way, associativity of composition can be now derived as a consequence of us wanting this Hom thing to be a functor. Even the identity law can be derived this way. At least one-sided identity law. Let's check this. So the other thing we need to do to get convinced that f is indeed a functor is to check that when I consider the identity morphism here from C to C, then the result will be an identity function. So I've got hom Cx there, I've got hom Cx here as well. And this function, which is f of the identity morphism, is our hom identity Cx. And what does it do? It takes x and maps it to x composed with identity C. And of course, x composed with identity C is equal to x, and therefore f of identity morphism is indeed an identity function. Fantastic. So what we've been able to show is that this procedure of assigning to a set C, the hom set Cx, this procedure is a functor. It's a functor from the opposite category of C to the category of X. But we have such a functor for every object X, right? F depends on X, yes? F is given by hom. One often writes this functor as hom dash X because X is fixed here. And to compute the values of the functor, you just need to substitute certain things in the first component, whether it's an object or a morphism. So f depends on x. For every object x, we have a functor. So basically, we're representing every object x as a functor to the category of sets, which we can think of it as a variable set. So every value of the functor is a specific set, but this set can change depending on which C we choose. And the change of these sets is governed by these links between them, which are specified by arrows between the objects C prime and C. So that's the idea of a variable set. So every object X becomes a variable set. So I can think of every object as a variable set. Can I think of a morphism between objects as some kind of transformation of variable sets? In fact, I can. So let's now consider two different objects, X and X prime. Each of them give rise to a functor. So the first functor will be hom dash X. The other functor will be hom dash X prime. So we are now considering two objects, X and X prime. The intuition here, once again, is that I'm trying my best to view an object X as a set. I don't view it literally as a set. I view it as a slightly more generalized kind of a set, a variable set. And now I want to view an arrow from X to X prime as a function between those generalized sets. Let's call this arrow. We've used F and G for arrows on the other side, so let's call this arrow H. So does a morphism H from X to X prime, does it give me a morphism between functors? Well, a morphism between functors is a natural transformation, right? So we're looking for a natural transformation, which we are going to denote by hom dash H. So let's remind ourselves what a natural transformation should do. When you have two functors, a natural transformation should be a passage from the values of one functor to the other, right? So for every object X, I will need a passage from every value of the functor. As a functor, hom dash X evaluates at objects of C op, right? In other words, objects of C. So one such value is hom Cx. And I need a way to link this up with the value of the other functor at the same object C. So let's draw this on the diagram. The question is what to do with an element X of Hom CX. If we have such an element, it means we'll have a morphism from C to X called X. And now I'm looking for an element of Hom CX prime. And of course, there is an obvious answer what to do here. We take the composite of H and X. And notice that this time composition is taking on the other place. It's taking place on the other side, right? Before we were attaching F on the right side to X, but now we're attaching the H on the left side to X. So X will map to HX. Intuitively, if I think of X as an element of capital X, I can think of H as a function, which what it does, it does this. H of X equals H composed with X. So evaluation of a function at an element now becomes an instance of composition of morphisms. Okay, so that's what each Hom CH does. So we have a family of maps, Hom CH, one for every C, running from Hom CX to Hom CX prime. This family is indexed by the objects of the category C up, which are the same as objects of the category C. What we want to do now is to get convinced that this family satisfies the requirement of being a natural transformation. There is a certain square that must commute for every change of C, right? So what is the condition for naturality of a family of maps between values of two functors? Every time I have two objects, C and C prime, and a morphism between them, if I evaluate, so I actually want to draw this now in a horizontal way. If I evaluate the functor, if I evaluate the functor dysmorphism, the first functor dysmorphism, I'm going to get Hom C X. The first functor will be given by the X, right? So Hom CX going to Hom CF, by Hom CF, it's going to Hom C prime X. I can also evaluate the second functor at that same morphism. So it will be going from Hom CX prime to Hom, sorry, I made a mistake there, right? This should have been Hom FX. And here we'll have Fx prime. So when I have two different ways of evaluating the morphism according to the two different functors, the components of the natural transformation, these maps that connect the values of the functors, must make this diagram commute. That's the requirement for something to be natural transformation, right? So here we have this Hom CH, and there we have Hom C prime H, and that must commute for every H. So I have X and X prime here with an H. So basically what I get is that for every F and every H, this square must commute. And to check this, let's recall what morphisms in C op are. They are morphisms in C in reverse direction. So F will actually be morphism in C from C prime to C. And now we pick an element of Hom Cx. That will be an arrow from C to X. If I map this thing down here by Hom CH, it will map to, remember, the natural transformation. Well, it's not a natural transformation yet, but the thing we are trying to prove is a natural transformation. It attaches the H on the left side of the variable. In other words, it composes this X with that H there. So we'll get HX here. And then if I try to map that by the other function, I'm going to be attaching their F on the right side, right? So I'm going to be composing this F with the composite XH. And we're going to get HX with F on the right side. Now, if I chase the same element along the diagram, along the top right part of the diagram, I'm first mapping this case, I'm first mapping X to XF, attaching F on the right side, and then mapping that result to attaching H on the left side. So on this left-hand side diagram, what we're doing here is we first compose H and X. We get an arrow here, HX. Then we compose this thing with F. So this will be HXF. And the other path was first compose X with F. So we'll get XF. And then compose that with H. So we get H composed with XF. And of course, these two composites are equal because of associativity of composition. So once again, associativity of composition is exactly what we need here. So we've now convinced ourselves that we have a natural transformation from between these two Hom functors. And so for every object X, we have a Hom functor, a variable set. And for every morphism between the X's, we have a corresponding morphism, a natural transformation between the corresponding functors. But once again, what does that mean? Doesn't that mean that we have a certain functor that's taking place here, that assigning to object X the corresponding variable set, and to morphism H a natural transformation between those variable sets? So to set this up as a functor, first we need to know where the values of the functor will lie. I mean, this functor will clearly be a functor from the category C, because this part here lives inside the category C. But what about its values? The values of the functor will lie in this picture, right? So where the arrows, the functors, are seen as objects, and morphisms between objects are natural transformations. Natural transformations compose. You can compose two natural transformations to get a natural transformation. I don't remember if we explicitly did this exercise or not, but it's a very easy exercise to do. And also for every functor, we always have an identity natural transformation, a natural transformation that goes from that functor to itself, which will be given simply by the family of identity maps. So functors from C op to set will form a category. It's called the functor category. And we will then get a functor from C going all the way to this functor category C, which we will write as set to the power C op. This is the functor category. Which means that objects of this category are functors from COP to set, and morphisms are natural transformations between those functors. What does our functor do? For every x, to every x, it assigns the functor hom dash x, and to every morphism h, it assigns the natural transformation hom dash h. This functor has a special name. It's called the Yoneda embedding. It's written by Y. And the reason why it's called Yoneda embedding is because a certain mathematician, Yoneda, discovered the importance of this functor. There is philosophical importance and practical importance. The philosophical importance is that we are really kind of regarding this category here as the category of generalized sets, maybe more precisely variable sets, but we're thinking of a variable set as a kind of generalized set. So we don't really want to distinguish too much between this and the category of sets. So it's almost like a more advanced version of the category of sets. And of course, intuitively, the notion of variable sets shouldn't be too surprising, because in real life, nothing is permanent, right? And you can think of something changing over time as a variable set, a set of data that changes over time. So time would be, in this model, the domain of the functors will be the time category, where objects are instances of time and morphisms represent change of time. So intuitively, this is, as I said, like an advanced version of the category of sets. And now what we're saying here is that every category can be seen to live inside these more advanced version of the category of sets. In fact, the Yoneda embedding here, the functor y, has all the suitable properties in order for us to really think of this setup as C living inside there. We will discover that y, for example, is injective, not only on objects, but also on morphisms. And moreover, it will also preserve a lot of things. A lot of properties will be, and constructions, not properties, but rather constructions will be preserved, but even properties will be preserved. And furthermore, not just that properties will be preserved, the functor y will clarify for us the essence of some of the properties that we've identified in an abstract category. Just to give you an example of this, let's take the property of a morphism being a monomorphism, something that we've talked about a couple of times already. So I want to show you now that I actually want to prove the following theorem. A morphism M from X to X prime is a monomorphism if and only if the value of y at M, so this natural transformation, I want to say is an injective function, but we haven't defined what an injective function is in this category. But thinking of it as a category of variable sets, let's say that a natural transformation will be injective if each of its components are injective. So once I fix my parameter for the variable set, I want the resulting function to be injective. So if and only if this thing at each object C, which will be a natural transformation from, sorry, it will now no longer be a natural transformation, it will be a function from hom CX to hom CX prime, if only that thing is injective for every object C in the category C. You will now very soon see that this is not just a theorem, it's actually the very definition of a monomorphism. Let me remind you that the notion of a monomorphism was introduced as an abstraction of an injective function. Monomorphisms in the category of sets are exactly the injective functions. And moreover, the definition of a monomorphism resembled very much the definition of an injective function. And now this similarity will become even more apparent as soon as I write down what it means for this thing, which is nothing other than hom CM, right, to be injective function. So hom CM from hom CX to hom CX prime is what? It's a function that maps an element X to mx, right? So writing down injectivity of this function is writing the following down. So injectivity says that if the value of the function at one element is equal to its value at another element, right? In other words, if mx is equal to mx prime, then those elements must be equal. That's exactly the definition of a monomorphism. That's exactly how we define a monomorphism, right? So I've got my x and x prime. And the definition of a monomorphism stated that if mx equals mx prime, then x will equal x prime. Now, there is another important fact that in this category of variable sets, monomorphisms are exactly those natural transformations whose every component is an injective function. So let's make a note of this. I'm not going to prove this now, but we just make a note of it. In fact, YMC being injective, for every C is equivalent to YM being a monomorphism in the category set COP. This is actually a general phenomenon of functor categories. You can even establish this fact if you replace the category of sets with another category that has suitable properties. that monomorphisms in the functor category are exactly those natural transformations whose each individual component morphism is a monomorphism in the codomain category, as long as codomain category is good enough, which it is so for the category of sets. So that does mean that, I mean, this restatement, the green restatement of this theorem does mean that the functor Y not only preserves monomorphism, but it also reflects them. So something will be monomorphism on this side if and only if it will be monomorphism on that side. So that's one example of why Yoneda embedding is useful. You want to prove something is a monomorphism in your category, right? You don't know how to prove that, but you know how to prove that if your setup was in the category of sets, because you worked it out in the language of elements, how to prove that that function you want to be injective is injective. Now the Yoneda embedding will allow you to transport your problem from the category C to this category, which looks very much like the category of sets. And then you can use your experience of how to prove that theorem using sets, using elements. And if the theorem says that something is a monomorphism, then because of this theorem here, proving it that it's a monomorphism on that side will give us that it's a monomorphism on this side. A theorem like this is called a representation theorem, when you are taking your abstract structure and representing it as a kind of substructure of a more concrete and hence more complex structure. And it's fantastic that even abstract categories can be represented in this way as subcategories of categories of variable sets. Another notion that gets completely clarified with Yoneda embedding is the notion of product of two objects. So let's look at that. I'm not going to formulate it as a theorem, I'm just going to illustrate it like I did here in the proof of the previous theorem. So let's look at the idea of the definition of product of two objects in a category. So what does it say? It says that if I'm given two objects X and Y, a product must be an object of the category. It must come together with two maps, pi1 and pi2, two morphisms, right? And it must have the property that for every object C, and for any two morphisms X and Y, there exists unique morphism here, let's call it Z, such that pi1Z is X and pi2Z is Y. Okay, now let's apply our intuition, our language for generalized elements. So let's rephrase this thing in the language of generalized elements. What are we saying? We're saying that a product is such an object together with two morphisms that if I take a generalized element of X, namely small x, and I take a generalized element of Y, namely small y, and they're parameterized by the same object C, then the pair XY, which is basically a representation of my Z, right? Because since I'm saying it's unique, Z is unique, right? I can write this as the pair XY. In fact, that's how I write this unique Z in the notion of a product. So I'm basically saying that the generalized elements of the product are pairs of generalized elements of each component, which means that as a generalized set, this is the Cartesian product of the sets X and Y. So this analogy is actually can be formalized nicely. So what I'm trying to say is that requiring this condition is equivalent to the following. So we take Hom Cx, we take its Cartesian product with Hom Cy, and then we take Hom Cx cross y. And I'm going to have a map running this way. What will this map be? It's a map that assigns to every z, it assigns the ordered pair pi1z and pi2z. Okay. So this is a very specific map that was created out of the projection maps pi1 and pi2. And now, once I've specified this map, it turns out that the definition of product is literally equivalent to this specific map being a bijection. But of course, if this is a bijection, it kind of tells me that x cross y as a generalized set is essentially the same thing as the Cartesian product of x and y as generalized sets. So why is it the same as this map being a bijection? Let's explore what it means for this map to be a bijection. Injectivity would say that if z and z prime map to the same spot, namely if pi1z equals pi1z prime and pi2z equals pi2z prime, right? Then they must be equal. So this must imply z equals z prime. If I look back at this diagram, this is exactly saying that there is at most one z for every x and y, right? Why? Because if there was another one, then it's exactly this injectivity property that would force the two to be equal if they have the same x and y. So thinking of this thing here as x and that thing there is y. So more formally, if I want to link these two, because I've stated this in a slightly different language where I was saying, starting with x and y and saying that is unique z, I could have also started with z and said that every two different z's, if after composing them with pi1 and pi2, they give me the same x and y, then they must be equal, and that will be the uniqueness part of this condition. And the existence part will say that every x and y have such a z, and that's exactly surjectivity of the function. So if I have an arbitrary xy here, an element of this Cartesian product, I'm now requiring this to be a value of this function at some z. So there must exist a z such that this is equal to pi1z, pi2z, right? And that's exactly the condition here, that such a z must exist. These are the same equalities that we would need to establish this equality of pairs component-wise, yeah? So this function being a bijection is basically the definition of product of two objects. But once again, we now can recast this fact as a statement that inside the so because this is happening for every fixed object C, it will happen at the level of natural transformations. It will turn out that the natural transformation hom dash x cross y, sorry, the functor hom dash x cross y is naturally isomorphic to the product of those two functors, where natural isomorphism is just a natural transformation, which is an isomorphism at each component, which is the same as to say that there is an inverse natural transformation. Where the product of two functors is given component-wise, like multiplication of two real valued functions is given by multiplying values. the same way, we can define product of two functions to be component-wise product of two functors to be component-wise product of those functors. So this is a natural isomorphism. I mean, in other words, we're kind of saying that we can now use the Yoneda embedding to recover the notional product here. So a product in C is a diagram such that when we apply Yoneda embedding to it, that we get a diagram of generalized sets. That diagram of generalized sets is a product diagram for generalized sets. In other words, it's a generalized Cartesian product. So, I mean, it is not the purpose of this lecture to go in such thorough detail of the properties of the functor y. I just wanted to give you an insight where this topic leads to. There are other things we're going to do today. We're going to come back to this later on with a bit more advanced toolkit to efficiently write out the proofs of the claimed results here, and also to define things properly in the functor categories and so on. But what I said here about monomorphisms and products is actually a general fact, and that will be also true for arbitrary limits. So it will turn out that the Yoneda embedding preserves and reflects arbitrary limits, but it doesn't preserve and reflect colimits. So if your category theory is such that the things you do in a category are all expressible in the language of limits, and these are products, the terminal object is also a special kind of a limit. Then there are things that we haven't discussed yet, pullbacks and equalizers and so on. So if your category theory you're doing inside a category C is completely expressible in terms of limits, then you might as well be working basically with your objects being sets and with your morphisms being functions, except that they're generalized sets and generalized functions. But working in this functor category most often reduces to working with individual values of those functors, which are the actual sets, and for transformations, they become the actual functions and so on. I want to show you an example of this application that working inside the category translates to working with sets and functions through the Yoneda embedding. But I'm going to show this to you without invoking this kind of heavy machinery of a functor going to a functor category. So I'm going to show it to you in a primitive language, staying inside the category C and talking about arrows into an object as elements of that object. But everything I'm going to say in that primitive language can be recast in a more advanced language by transporting the problem from the category C to this category of variable sets, and then reducing the problem to specific sets and functions by taking at a time considering values of the functors involved. So one value at each time. Okay, so the problem I'm going to use as an example is the following one. So let's prove that x cross y is isomorphic to y cross x. What is an isomorphism between objects? Let me remind you that an isomorphism from A to B is a morphism F for which there is an inverse morphism. Let me call this I. So there must be something else called I minus 1, such that the composite of I with I minus 1 equals 1b, and I minus 1 composed with I equals 1a. So we're going to establish that there is an I going from x cross y to y cross x, and that there is I minus 1 going from y cross x to x cross y. But we are not going to do it directly in an abstract category. We are first going to do it inside the category of sets, where the construction of this I and I minus 1 is pretty obvious. And then we're going to see how we can repeat that argument that we will use for sets. How we can repeat that in the language of generalized elements, and hence in an abstract category. And then finally, we will see that this repeated argument would actually give us an actual argument in an abstract category as well. Although the need for such an argument would not be necessary after we develop fully the power of Yoneda embedding, because Yoneda embedding will tell us basically that because I was able to prove it for generalized sets, and that reduces just to proving it for sets, it must be true in an abstract category as well. So what do we do with sets? If x and y are sets, well then, if x and y are sets, then x cross y is what? It's the set of ordered pairs, right? Where x is an element of x and y is an element of y. Y cross x is a set of ordered pairs yx, where y is an element of y and x is an element of x. And now if I'm looking for an isomorphism between them, which is the same as a bijection between these two sets, isomorphism in the category of sets is the same as a bijection, right? So to specify a map I and an I inverse, I need to specify what happens to these ordered pairs. Sorry, I will go this way and I inverse will go backwards there. So I take an ordered pair xy and I map it to yx, right? And the inverse will take an ordered pair yx and map it back to xy. Let's check these two maps are inverses of each other. That's a very trivial thing to check. If xy maps to yx, well, it does map to yx, and then mapping it back, we get exactly xy. So this is applying I first and then I inverse. And then if I apply I inverse first, which is of course a symmetric argument thanks to the fact that roles of x and y can be interchanged, then I get this, and then this maps back to yx by I. So the proof is done. Let's see now how we could use this, how we could adapt this proof for generalized elements. Well, first, let's begin by adapting the notation. So as a generalized set, what is x cross y? And I'm going to use still the same set theoretic notation, but I'm going to use a different color to emphasize that now this time it's a generalized set. As a generalized set, we already explained it here. As a generalized set, in other words, for each fixed C, the set is essentially the same as the Cartesian product, right? So we're going to think of it as the set of ordered pairs then, where x is a generalized element of x, but now I'm going to put a subscript C here. I'm going to explain in a moment what I mean by that, and y is a generalized element of. So yeah, let me not introduce new notation to make things a bit more straightforward. So let's actually write it the way we intended to write it. So x being a generalized element of x with parameter c means that x is an arrow from c to x, and y is an arrow from c to y. So it's a set of ordered pairs of such arrows, and this is a generalized set. So but there is a C involved here, right? So I have to say that maybe I should put a subscript C here, because what I'm really describing here is hom C x cross y. And to make this notation legitimate, because so far we only had a bijection between that and that, so we didn't have quite equality there, right? But we can fix that problem by actually using the ordered pair notation for the unique Z that must exist here. And then this ordered pair xy indeed becomes a morphism from C to x cross y, parameterized by C, but we know that there is a unique morphism making this diagram commutative. So it's the morphism that with pi1 maps to x and with pi2 maps to y, and we know that such a thing is unique, so we might as well just use this ordered pair notation for it. So then what I wrote here becomes quite a legitimate formula, which just tells me that so thinking of x cross y as a generalized set, I would rather have perhaps it written like this, hom C that, and then removing it from there. So we now turned basically this expansion of the Cartesian product, we've turned it into a description of hom sets going into x cross y, which intuitively we still think of it as some kind of generalized set, well, an actual set once the parameter C is fixed, of ordered pairs. In a similar way, I'm going to have this hom C description of y cross x. So as a generalized set, it consists of ordered pairs yx, where y is an arrow from C to y, and x is an arrow from x to C to y, C to x, sorry. And now what I need to do is to describe this isomorphism, right? And I kind of want to say that let's consider the isomorphism that will map xy to yx. But remember, a function between generalized between these generalized sets, it must be parameterized by an arrow in the category. If it's not given by hom C I for some morphism I in the category, if it's not given like that, then maybe inside the functor category set C op, these two things will indeed be bijective, but x cross y and y cross x inside the category C might not be isomorphism. We actually need the isomorphism I, right? So how can we get the definition of the isomorphism I by knowing what I wanted to do in the language of generalized elements? I basically want I want hom Ci of the pair xy to equal the pair yx. I want that, right? But wanting that is the same as wanting that I composed with x, the pair xy, must equal to the pair yx. Why are these two things the same? Because that's how hom Ci is defined. It attaches the morphism to the left side of my other morphism. So I want this to happen, right? And then I also want another thing, which will be I inverse, which I want to do the opposite. I also want I inverse evaluated at yx to give me xy. And in the case of sets, I have what I want because when I write down what I want, it gives me the definition of the function, right? So when I write down, I want I of xy to equal yx, then that's the definition of the function I want. The question here is, can the same work in this context where writing down what I want will give me the definition of I? It would if I were able to choose x and y in such a way that this composite, that this pair xy is identity morphism. Because if this turns out to be identity morphism, right, then I composed with the identity morphism will be I. And so this will be the definition of I. I will be whatever will be on the right side. So now a question to those who are here. Do you think we will be able to find x and y in such a way that the ordered pair xy becomes an identity morphism? So let's draw a diagram to make it a bit easier figuring out this question. So if I want the ordered pair xy to be identity morphism, it means my C needs to be x cross y. So I'm looking for identity morphism here in the role of pair xy. The question is, what should x and y be? So x and y should be such things that would make this diagram commutative, right? So this should be x, and that should be y. So what do you think should x and y be? For which x and y is this induced map here, the one coming out from the definition of a product, exactly the identity morphism? Any thoughts on this?
I would suppose they would be the projection maps as well. So x would be pi1 and y would be pi2.
That's an interesting suggestion. Let's verify if that really gives us the answer. If I do put pi1 and pi2 here, why will this map be identity map? Well, the definition of this map is that it's the unique such that the diagram commutes. And the identity map does make the diagram commute, doesn't it? Because identity composed with pi1 is pi1 and identity composed with pi2 is pi2. By definition of the product, there must be only one such thing that makes it commute. So the xy, the unique thing, must then be the identity morphism. So indeed it works. So then my equation becomes I composed with pi1 comma pi2 equals I composed with identity of that object x cross y. So I can rather maybe write this on the other side. And this is I. And so on the right side, we'll have pi2 comma pi1. And so what I wanted now, the thing I wanted did give me a definition for the morphism. In the same way, in an exactly symmetric way, I inverse will be equal to what? Now I want yx to be identity, right? So then it must be pi1, pi2. No, sorry. Let's do it more carefully. So I composed with identity. So I inverse equals I inverse composed with identity. And we know that identity is given by pi1, pi2. And if I put it like that, again, it will reverse. So it will be the same pi2, pi1. So in fact, this morphism is inverse of itself, which is shouldn't be too surprising because exactly the same thing happened in the case of sets, right? The functions I and I inverse are actually the same function. They are the function that swap components of an ordered pair. I think for a moment I was stupid enough not to realize that. Anyway, so I and I inverse are both the same morphism given by pi2, pi1. Now I want to check that they are really inverses of each other, right? So I could check this for generalized elements, couldn't I? I inverse applied to xy, which in the language of generalized elements means I inverse composed with xy, equals what? Equals I inverse composed with yx, and that equals xy, right? So you see, xy does return to its original place. But that only means that I've proved that I inverse composed with xy equals xy. I don't want that. I want something stronger. I want I inverse composed with I to be identity of x cross y. Will I be able to conclude this from having proved that for arbitrary x and y? Any thoughts on that? How to go from there to here?
I have a suggestion.
Yes.
So we could just place the brackets around I inverse composed with I in the top equation, and since there's a unique function that composed with some arbitrary xy gives xy back, and that is the identity morphism.
How do we know that there is unique such function?
Isn't that one of the axioms on a category?
No, I don't recall such an axiom on the category.
Okay, well then that doesn't work.
Is there any way for us to conclude from this fact, which has been established for arbitrary x and y, to conclude from there to conclude this one?
Sorry, can you hear me?
Yes, yes. Yes, I can.
We're taking x comma y as an arrow, is it? Oh. Yeah. I'm saying taking x comma y as an arrow.
X comma y is an arrow, yes.
If we apply associativity using brackets there, let's say we say that is equal to I inverse brackets I composed with a pair, then we apply the I.
Yeah, that's what we did on this side. That's how we got this equality, right?
That's what we did on this side, yeah.
But now I want to prove that I have an isomorphism inside the category. So I want to prove this.
Yeah.
The question is how to get this from that one.
Yeah, okay. But if we reconnect the brackets with what is this?
Sorry, Charles, I couldn't hear that.
If we start with brackets all around the I inverse composed with the I and rearrange them, does it not get us to the same thing?
I don't think so, because that's what we tried to do here. So we had brackets this way. And if I rearrange and put brackets there, then I don't know how to proceed because I know nothing about this composite. I actually want to prove that that composite is identity.
Okay. Well.
So the proof I know in the case of sets, which I've adapted to generalized sets, of proving that I and I inverse are inverses, this is the proof for sets, right? The proof I know, I translate it to a general category. It gives me this proof. It gives me that I inverse I composed with xy equals xy. But it doesn't seem to give me what I want. I want to prove this, right? Which is a stronger property, because I mean, if I inverse I was identity, then indeed that composed with xy would have been xy. So it seems to give me something a bit weaker than what I want. Is it maybe possible that this weaker fact, in fact, does encompass this as well? Because remember, this fact is true for arbitrary x and y. Any further thoughts from anyone else?
Yeah, I was thinking now that what if we took X to be the identity morphism on X and Y to be the identity morphism on Y? And then that would...
How can that be? Because X and Y, even though I said they're arbitrary, they must be parameterized by the same C. They must have the same domain. The objects X and Y might be different from each other. Isn't this problem similar to the problem we encountered here, where we had a definition of I in terms of how it should compose with things, but now we want a definition of I explicitly of what it should be. And to get that from this definition, which was working for arbitrary X and Y, we were able to find a suitable X and a suitable Y, and extract from this, in a special case of this equality, extract from that the definition of I. Could we not apply a similar strategy of extracting this as a special case of that with a suitable choice of X and Y? My question is so easy that the fact that it wasn't obvious already now what the answer should be means that either I'm explaining these things in a very bad way, or the concept is so new that it takes time to digest it.
So do we do just exactly the same thing as before?
Yes. We can do exactly the same thing as before. We know that this is true for every X and Y, so we could apply it in the case when X and Y are pi1 and pi2. We now know this, but pi1, pi2 map, we already remarked, is the identity map. So this will become identity morphism, and then that will become identity morphism as well. So then we will get this. So not only the language of generalized elements led us to actually identifying a candidate for an isomorphism in the category, in the abstract category, but it also led us to proving that it's an isomorphism. Of course, we need to do the other way around as well to prove that I with I inverse will be the other identity, well, the same identity, but that will follow exactly the same picture as this one. So something general is happening here. There is a general phenomenon that tells us that every time I will have a construction of an arrow or an object in the language of elements, and a proof that certain maps compose to the same map in the language of elements, every such time I will be able to adapt my proof or construction to my abstract category by this game of choosing specific representatives for the generalized elements, like we did here. And this is exactly the the general result where this story leads to is exactly the result of the thing that's called the Yoneda lemma, which will be establishing properties of the Yoneda embedding. I'm going to now focus on one particular aspect of this, namely the construction of a morphism I out of a natural transformation. So we had a natural transformation in mind. We wanted to map xy to yx. And then it turned out that this natural transformation does actually come from a certain morphism I by defining I this way. There is a general fact behind this, which is absolutely fascinating fact. And this general fact is basically part of what Yoneda lemma states. So the general fact is the following. Imagine you've got two objects, x and y. And let me call it x and x prime. Let's view them as generalized sets. So let's view them as these variable sets, the functor hom dash x and the functor hom dash x prime. And let's consider an arbitrary function between generalized sets. Of course, this means an arbitrary natural transformation. So n is a natural transformation. So all we know about n is that it's a natural transformation from there to there. It turns out that, okay, before I describe what it turns out, let me link this back to what we were doing before. So we already had such a setup where we had these two generalized sets, and we had a very specific type of candidate for a transformation, which was a function that we wanted to map xy to ix. And then from there, what did we do? We built an actual an actual morphism in the category for which this is the corresponding generalized function. So it turns out that for any natural transformation n, there will always exist, in fact, a unique f such that hom dash f equals exactly my natural transformation n. Once again, this fact has a significant philosophical interpretation and also practical. The practical one is the one we already exhibited. So if we knew about this fact, we no longer needed to carry out this argument. We could have said, okay, let's just check that this thing of swapping the order of pairs is a natural transformation. Then we know for sure that it will be of the form hom ci for some morphism I. So that would have been the practical use of this fact, which we used it, but we also explicitly gave the proof because we didn't know about the general fact yet. Now, the philosophical significance is that we're now saying that when I view my object as a set, right? Any function between these two sets that I can come up with, remember a function means not just an arbitrary family of maps, but the one that's a natural transformation between functors. It also, by the way, gives a good test to the notion of natural transformation. So any function between those generalized sets does arise from a morphism in the category. This is quite fascinating. You can map things any way you like from there to there. As long as it's a natural transformation, there will actually be a morphism that represents the transformation. How do we work out what f is? Well, we will follow a similar approach as we did here. We will first write down what should f do if there was such a thing. So if hom dash f was indeed n, then for each object c, hom cf of x would be what? would be fx, right? So this is what, sorry, it would not be fx. What am I talking about? Yeah, it would be fx, but at the same time, this fx would be the value of n, of the natural transformation n. The component of transformation we pick now is c, evaluated. So n being a natural transformation, it means that it's a family of maps, right? One for each c. So it maps hom cx to hom cx prime. So that's what a natural transformation is. It's not any family of maps. It's a family of maps that satisfies those naturality squares, right? So we are given that, and now we're saying that if there was an f for which hom dash f equals n, then that means that for every c and for every x being an arrow from c to f, we must have that fx equals nc of x, right? So this equality is nothing other than this equality, because n as a natural transformation is a family. This as a natural transformation is also a family. It's the family of CFs, right? From hom CX to hom CX prime, where C is an object in the category. And if I'm saying that these two families are equal, this one and that one, it means that each of the members of the families are equal. So these being equal to that, on the other hand, is that these are functions having the same values, because they certainly have the same domain and the same codomain, right? So I'm now saying that this evaluated at x must always be equal to that evaluated at x, but that evaluated at x is fx. So I'm saying that f composed with arbitrary x must always equal nc of x. Now we are facing a similar problem as before. Would we be able to determine f based on this information? So we basically, in the intuitive set theoretic language, we are saying here that we know how f composes with things. So knowing how f composes with things, does that determine f uniquely? This equality must be true for every x. So we are now trying to find a specific x for which this would give me an expression of what f should be as a morphism in the category. What do you think? What x should we choose? I'm sorry, I'm making a board a bit bigger now. So let's draw this thing on a diagram. We've got a C, we've got an X, we've got an X prime. And we don't have F yet, we want to build the F. The F that we're looking for must be such that every time I pick a morphism X, F composed with that X must be equal to the value of the natural transformation N at X. More precisely, the component of the natural transformation parameterized by C, the value of that component at X. And this I want to happen for every C and for every small x. What should F be? Does this determine F uniquely? Remember when we were looking for I as a morphism, we had a similar equation. We had I composed with this must be that. And what we said there, that if we take this to be identity, then maybe we can get I to be equal to something specific. So can we do something similar here? Okay, let me re-explain the context. So we're working in a category C. We have two objects, x and x prime. We consider the corresponding functors, and we have an abstract natural transformation between them, and we want to represent it as an arrow from x to x prime. And that means that we want to find an arrow f such that f composed with each x gives me nc of x. What should f be?
Can I make a suggestion?
Yes.
Should it be hom C, hom CF? Maybe.
Hom CF must equal to NC.
Yes.
So you're saying now f should be what?
I thought f would be hom CF, but as you just said, that
doesn't
would
make
be
sense
equal to
because
NC. Yeah.
It doesn't make sense because hom CF is a function and f is a morphism in the category.
Oh yes. Okay, I see.
We want f to behave the same way as hom CF. Yes, we want. That's what we wrote here. But now we want to find f.
Yes. Okay.
An actual morphism in the category. If it is so that I've confused you a little bit with too many arrows here, think about this very simply. In this equation, what is known and what is unknown? Unknown is f, and what is known is this part, and what's also known is that this equality is true for every x. I want to solve for f, right? Knowing that this is true for every x. So for every x from C to x, and now I realize I wrote nonsense here. This shouldn't be f, this should be x. For every x from C to x, I have this. And I want to extract from this a definition of f. Obviously, I will be looking for some specific value of x, right? Can I choose small x in such a way that this will give me an actual definition of f? Can't we do exactly the same thing as what we did before?
So would we choose x then to be the identity morphism?
Yeah.
No. Yeah.
Why not?
But shouldn't it work for any pairs of C and X? So
well, we first got an f, and now we will have to. I mean, the f, if f satisfies this, right, it must satisfy this for the identity morphism as well. There's no way out here. It must satisfy that, right? The other question is if such f will satisfy the more general equality as well or not, but that will be a further task to carry out. So a special instance of this diagram is when we put in this place of C, we put x, and in the place of small x, we put identity. Then we will have a specific thing here called nx of identity. And that should give rise to an f by just setting f to equal nx of the identity. So this equality, if such an f exists, that f is forced to equal to the value of the natural transformation at the identity morphism of x. But we also want the reverse. We want this specific f to fulfill the equality of the natural transformations NC and HOM-CF. In other words, we want this value to always equal that value, which is equivalent to saying that this equality should hold for every x. So we'll have to check now that it is true for every x from C to x that nx of identity x composed with x in fact equals nc of x. If this is really true, it will be quite an extraordinary fact, because it will mean that the values of the natural transformation are uniquely determined by a single value, namely the value of the transformation at identity morphism. So the entire information about the natural transformation is given by exactly one value, which is quite strange. It never happens with functions, right? Of course, that value is the magic value. It's the morphism F that represents my natural transformation as a morphism in the actual category. If we do all of this, this will be proving that there exists at least one such F, and then we will also want to prove that the F is unique. But I think uniqueness we already took care of, because since this must hold true for every X, in particular, it must hold for the identity morphism, and then the F is forced to be defined like this. So if the F that we propose to define like this works, it will definitely be unique, because we just have the equality for what F should be, right? And so then we would have proved that indeed for every n there is a unique F satisfying this. Once we check that the F we propose here, it fulfills this. The fact that the F we propose here fulfills this will turn out to be a consequence of the definition of a natural transformation. So let me draw this diagram of naturality for the natural transformation. I'm going to take identity morphism here, and the natural transformation, which now runs from hom CF to hom CX to hom CX prime, right? So I have two. Just a moment. I want to set this up correctly. So I'm going to first draw this equality as commutativity of a certain square, and then extract from it what the square should be. Composing with X on the right side is what? Is it's evaluating the functor at the morphism CX, right? There we go, this one. So consider this morphism. Then by applying the hom dash X functor, we get a map from hom XX to hom CX. This is the application of the hom dash X functor to the morphism X. What does it do? It maps every morphism here to the composite of that morphism with X. Then we have the natural transformation that runs vertically, where now we consider here the other functor, which is, what is the other functor? The other functor is hom dash X prime, right? So that one, and that one here, and here we have hom X prime. The vertical maps are my components of my natural transformation. So this is n component, X component of n, and that one is C component of n. I've drawn here nothing other than an instance of naturality square. This square must commute for every arrow X by definition of the natural transformation. Now I'm going to use that fact. Since I know this square commutes, I know that if I pick a specific element in here, and the element I'm going to pick will be identity morphism of X, which I definitely leaves there. And I'm going to chase this element around the square and see where it's mapped to by the right side, chasing it right or chasing it left. I know that it must map to the same place by both maps, but let's see what that place is. So identity of X mapped to the right by hom X, capital X function will be just a composite of identity of x with small x. So the diagram here, we've got identity of x there. Then this thing by n is mapped to, of course, this is equal to x, right? Because x composed with identity is x, and it's mapped to nc of x. On the other hand, on the left side, identity is mapped to nx of identity. And then it is further mapped to composing this with x being on the right, right? So it's mapped to nx identity composed with x, which is exactly the left side of our equality. You see, this equality is exactly an instance of this equality. When we pick identity x as the element here in this square, which is an instance of naturality property of the transformation n. And so because the square commutes, because we've got this equality for every x, we now know that if we define f in this way, then we actually have that hom dash f equals n. And because we were forced to define n in this way, such f is unique. So we've proved that this unique f indeed exists, and uniqueness part was kind of easy, but we proved that as well. So what we've done here is basically a general fact whose specific instance we already exhibited in the previous case. Let's formalize this as an actual theorem. The functor y going from C to this category is full and faithful. What does it mean for a functor to be full and faithful? It means exactly what we proved. But let's write these definitions out so that I will write them separately, and then together it means what we proved. What does it mean for a functor to be full? A functor f from a category C to a category X is full when for every C and C prime in the category C, the function from hom CC prime inside the category C to hom FC prime inside the category X, this function given by mapping an arrow f to the value of the functor at that arrow. So this function is surjective. So fullness means that if I start with two objects in the domain of my category, and I consider an arbitrary morphism between the values of the functor at those two objects, then there must be a morphism on the left side that maps to that one. It's exactly what we did here when we considered an arbitrary morphism between the values of the two functors, right? And we claim that that morphism comes from some morphism there. So the existence part was exactly fullness of the functor. And faithfulness is injectivity of the same map. So a functor is faithful when the same map is always injective. And together it gives bijective, which is what we proved here. We proved that there exists unique f that maps to n, which is to say that there is a bijection between this hom set, between the set of morphisms from x to x prime and the set of morphisms from hom dash x to hom dash x prime. So faithful means that just going to paste this one and replace surjective with injective. We will later come back to full and faithful functors. The notion of a full and faithful functor is in general very important. Full and faithfulness of a functor already, I said it's very important, and it's important because it has lots of useful properties. For example, it allows us to reflect isomorphisms, which would be a general version of the thing we proved here. So it turns out that if you have a full and faithful functor, and you've got two objects from your domain category, which there are mapped to two isomorphic objects, then your two objects in the domain category will be also isomorphic. And that will be a very general fact, which applied to this specific scenario would give us the isomorphism we were looking for between x cross y and y cross x, knowing that there is a bijection between the Cartesian products x cross y and y cross x. So the Yoneda embedding is full and faithful. And the other very important property of the Yoneda embedding, which we only gave some intuition to, we didn't prove it, and we're not going to prove it today, is that this functor preserves and reflects limits. So what does that mean? If you've got a diagram in C and you take its limit and you apply the functor, it's the same as first applying the functor to your diagram and then taking the limit in this category of generalized sets or variable sets. And reflection means that if you have a diagram that comes from C, have a cone over a diagram that comes from C, that cone turns out to be a limiting cone here, then it turns out that the cone originally was a limiting cone in C. And the fact that this preserves and reflects limits, the formal proof of this would require, as a stepping stone, the fact that it's full and faithful. Okay, so we are now reaching the end of this lecture, partially because I will have load shedding at 10 o'clock. I want to conclude with a kind of summary of what we did today and a philosophical remark. So going all the way back, we talked about generalized elements of objects, and we saw how each object of a category, of an abstract category, can be regarded as a kind of a variable set, where what makes the set vary is the parameter that is the domain of my generalized element. And then we saw that this intuition of viewing an object X as a variable set formalizes itself as a functor from an abstract category C to the functor category, the category of functors from C up to the category of sets. We further saw that this functor has useful properties. We said something here about injectivity and monomorphisms, but in fact, we didn't say this, but in fact, that fact about monomorphisms that we claimed there and partially proved can be obtained as a consequence of these two theorems, the full and faithfulness and preservation and reflection of limits. Again, this is something we will come back to in the future. So this functor Y, the Yoneda embedding, let me write this out explicitly. So this thing is called Yoneda embedding, has some very useful properties, and specifically the useful properties it has is that it's full and faithful, and that it preserves and reflects limits. Now, the philosophical remark I want to make is that we view this category as almost like a category that is almost behaving at almost the same way as the category of sets. We really view objects there as variable sets, where intuition for variable sets is very easy to motivate, and basically many things you know how to do with ordinary sets, you will be able to do with variable sets in a very straightforward way. And hence, we now have a representation theorem that tells us that every category C can be inserted into the category of variable sets. And the fact that this Y is an insertion is basically the full and faithfulness property. You see this local bijectivity property. In fact, it will turn out from this definition that, well, not from this definition, but it's not difficult to check that the functor Y is also, on top of being full and faithful, is also strictly injective on objects, which shouldn't be too surprising. I mean, these two functors can never be the same because, for example, one of the elements of a value of this functor is identity object of X, and that can never be found here because morphism in a category remembers its domain and codomain. So for X and X prime different, these will be different functors. So we can really think of this Yoneda embedding as an insertion of the category C into this category of generalized sets or variable sets. And the fact that it has useful properties means that a lot of things, a lot of problems that I want to solve in an abstract category, or theorems I want to prove there, or even concepts I want to develop there in an abstract category, can now be done by taking the solution to that problem or the construction of that concept in the category of sets, adapting it to variable sets, which is a straightforward process, and then making use of the properties of this functor to carry over this concrete description of my problem or solution of my problem or construction of an entity, and carry it over and get the solution of the problem in an abstract category. The problems that we will be able to solve this way will have to be expressed very much in terms of limits, because the functor does preserve and reflect limits, but it does not preserve and reflect colimits. And there is no functor that would preserve and reflect both limits and colimits and would nicely embed a category into the category of sets. So if my category theory is such that I'm using both limits and colimits, right? Then I won't be able to make use of this luxury anymore. But if I'm only using one kind of limit, either limits or colimits, then I can make use of this luxury, and it's a very practical tool indeed. Many theorems in category theory can be obtained by applying this a piece of luxury. Okay, of course, a more detailed selection of examples of such applications is still to come in our course. We gave a little bit of insight in this lecture by explaining how we could have possibly been able to even discover the notion of a product of two objects by those nice properties of the Yoneda embedding. So that's in terms of coming up with a concept, and in terms of proving a theorem or solving a problem, we described how we could adapt the proof that Cartesian product X cross Y is bijective to the Cartesian product Y cross X to get an isomorphism between X cross Y and Y cross X in an abstract category.